Hey, I am here to show you how to distinguish between good and bad data by actually inspecting the data from the different hyperspectral suppliers. The process, of course, of inspecting the data is the first step about looking into the quality. You can, of course, do way more in-depth analysis than what I'm showing you now. If you want to read more about or learn more about key quality parameters in hyperspectral systems, follow the link coming here. There you will see a 1-hour presentation about key quality parameters in hyperspectral systems. Okay, let's start inspecting some data. Okay, let's start with an airborne image. It's a Veneer 1800 system flown over an area in Italy. It's 5 flight lines stitched together. It's a quite hilly area, so the pixel size changes on different places in the field of view. So the first obvious thing to inspect, right, is sharpness. So just to see that it's sharp per pixel, spatially first. So you can go around inspecting that, looking at the details. You can also see the, let's see, this is number 8. So you can look at the zoom as well, which is here. Yeah, so inspect that all the borders, everything is sharp. Different places in the field of view, right? I will come back to that also later when we go to the drone system. Then it's about spectral sharpness. For visible near infrared range, it's this feature you see here, the 760 feature. It's a very sharp absorption features for oxygen. This one is good to use to see the sharpness. For a blurry spectral system, this will not be as deep. It can stop up here already, right? So the sharper, the deeper this feature is, the higher spectral resolution, or the better spectral resolution you have. Let's go to some vegetation. The important thing here is also, like, don't only do this for the default RGB bands, right? Do it for all the different channels. Go through the spectral channels. Now I just changed the default RGB bands to some other bands. So you should actually step through the bands, just look at that the sharpness is looks the same everywhere. A very common problem from different suppliers is that they promise a specific spectral range of the system. For example, like this is from 410 to 992, or from 400 to 1000. And if you go into the data and you inspect the first and the last band in this range, which is typically, or the beginning of the spectra at 400, at the end at 1000, it's typically the problematic areas. And many suppliers have no energy in these bands. So meaning they have a problem with their relative spectral response function of the whole system. So just to visualize that, I will show it here. If we go into this, just show the first band, right? Band 1 is 440 nanometers. So if you see on this system here, it is still energy here. You can clearly see it's not a grainy, noisy image, and it's still as sharp as it was before. Then let's go to the last band. I think that is 992 for this one here. And NV enhances this the way it seems fit, so let's change the enhancement. Yeah, so again, you have energy, you have sharpness, yeah, which is good. Yeah, that was a simple test just to check for sharpness. Let's move over to some UAV data. I have a scene here from Cooperite, which I think is, no, there you have it. Yeah, so here you have the Cooperite data. is again now 6 flight lines merged together, or mosaic together. You can clearly see that here because of the there's a small area here where there were no overlap, so you can see there's a gap. This is data from a Mjolnir VS620. That's our co-aligned drone system. This has 2 optical systems, one from 400,000, one from 1,000 to 2,500, and the optical axes are parallel, and they are basically looking at the exact same place in the scene. So then you can merge this perfectly together right afterwards. So I will show here, for example, let's go to the VRay, show some bands in the VRay here. Copyright Ridge is a very known area in Nevada that is used for a lot of geology, which you can clearly see here. Just in the false color RGB, you see there is a lot of different mineralogy here. So when you are inspecting data from a provider that sells the full range, it's always good to see if they have a co-registration issue, right? And that the georeferences is good. So let's start with the georeferencing, right? A very common problem is that when you try to mosaic several flight lines together, you will have it will not be overlapping perfectly. There's many reasons for that. Some suppliers don't even supply a sensor model with their cameras, which then you will never be able to get a good georeferencing. You need a high accuracy surface model. You need your cameras bore sighted. You need your LiDAR bore sighted. When you have full control over all these things, then you have the possibility to make some good data products, right? So for example, in this one here, you cannot see the stitching between the flight lines. So here you can see one starts and the other stops, right? You can browse around the different areas and just inspect it visually. Good. That's the VS system. Let's open an Airborne sphere image. Default RGB to new. No, this is a very long image, or at least to show here. Great. So yeah, as I said, this is a 384. This is kind of our best seller, together with the Veneer 1800 for airborne applications. Over the last year, of course, the Sphere 640 has taken over quite a lot. But let's see now. Let's use this data set to look at Straylight. When you have a sphere system, right, you expect, you will have 3 large water absorption areas. This is the one here at almost at 1200. You have one at 1400 and at 1900. If you want to see if you have an obvious Straylight problem, you can use those features. So, for example, if I put all the false color RGB bands now to the 1900 feature, there shouldn't be any energy there, right? Because that means it's Straylight. So as you can see here, there is no energy, or very little information at least. So that's anyway. If you see a lot of data here, you see some structure on some side of the field of view, right? That means that probably the supplier has a Straylight problem. For the visible range, if you go back to that, right, to the drone data or the data from Parma, what you typically will see is maybe bluish haze, for example, in the visible range. So that's a very common problem in many imagers, is that they have a lot of Straylight in the blue region. So look also for that in the data. Also, of course, I haven't mentioned that yet, but striping in the data, that's also something to look for. HySpec doesn't have any problem with striping because we have a patented optical design that will basically eliminate that problem. But many supplier has that, and please look for that as well. Okay, so that's sphere data. Let's also have a look actually at smile in your data. So smile in your data means basically that the spectral vector in one place in the field of view shifts from one place to another place in the field of view. Of course, that's a very bad situation, because then you cannot use, for example, if you use a model that you have made, it will not work the same everywhere in the field of view, right? To inspect that, we will go over to another data file. Let's see. We can use, for example, the one sample here. Yeah, this is data from 30 centimeter lens with our V640, our new V640. So this has 640 spatial pixels. So if you want to see if there's any shift in the spectral vector, one way of doing it is you can plot here, for example, the spectral vector. You can collect spectra. So if you collect spectra now from different places in the field of view, they should be on the same place, right? If I go here, go here, 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 I can move here, here, and here. So this one, as you can see, falls in the same band. Of course, you will probably not be able to see a kind of a 10% of a band shift here, right? But this is to give, I have seen some bad data out there, right? And especially for the close-up lenses, right? There are many of the suppliers here, when they make bad for optics for their spectrographs, have smile in one or two bands, right? So you will then clearly see that there's a shift different places in the field of view. This is a simple way just to detect if you have any smile in your system at all, or any visible smile. Keystone, the way to visualize or to look at keystone to see if you have any, it's very hard to detect, or just by your eyes looking at keystone, if you have low amounts of keystone. Like in the Suite 384, we have, of course, less than 10% of keystone, so you will not see it in the image. But some suppliers actually have, they say plus minus 35%, but that means actually 70% keystone. And then if you have a building like this, right, you will actually see discoloring on the edges of the buildings due to keystone, right? And I just want to comment here on this image as well. We always use nearest neighbor resampling when we are geocoding or orthorectifying the image, which this has been done, right? That means that the image will look more kind of coarse geometrically, because we want to preserve the original spectral data from the raw cube. That's why we do this. So here the spectral integrity is intact. Of course, if you want to make the nicest looking image, you can use other resampling methods like bilinear, for example, which will make the image look better visually. Yeah. So here, yeah, I can clearly see that the rooftops are quite different spectral signatures. Some are red with this band, some are gray, and so on. But you will not see any discoloring or stuff like that, which is due to keystone. But in many systems, you actually can inspect that in a data itself. Okay, let's take it one more step. We looked now at sharpness. We have looked at keystone and smile in data. We have inspected Straylight in the 1900 region. Let's take it one step further, for example, with this VRay data. One way of finding out if you have any unphysical noise sources is to run the data through an MNF. So we can do that now with this data. So let's see here if I should run an MNF on this data. Forward, estimate, sample 2. Let's do a spatial subset so we don't take the whole thing. We don't want to have the we can take maybe like this. Okay. Here you can also select a mask. In HySpecs, what we do, for example, with saturated pixels, is that we flag them. This is a very important thing, right? Because you need to know if your pixel originally in your raw data was saturated or not. So through the whole process, we flag it. When it's converted to radians, it's flagged as the value 2, and that's in the unit watts per nanometer stereo square meter. So in those units, value 2 in any of the bands means that it's saturated. And that means it's very easy to make a mask to remove the saturated pixels. I don't think there's any in this image, so we will not do that here. Just make some names. And here is now calculating MNF. So what you should look for now in the data is some weird spatial structure in your MNF bands, because that can indicate you can find spectral calibration problems. You can find a lot of resampling errors if the companies are doing resampling. A lot of problems can be identified actually in MNF. So let's open the first band. This is the first MNF band. Here looks normal. Let's go to the second. Again, looks normal. Third. So if you start to see some features here, some spatial features that you see is in the image itself, it's not on the object, then you should be concerned. So again, this is for our 3640 system. So what you should start to see when you move higher up here, that white noise basically takes over. But when you get this white noise, that is normal. But there should be no kind of spatial features before you get to the white noise features. So that's a way to also find unphysical noise sources in your data. So to sum up, always ask for sample data from all the suppliers. Ask for relevant sample data. If you are buying an airborne system, ask for an airborne system. If you're buying industrial or lab system, ask for that kind of data and inspect it with some simple steps as I just showed you. Ask for test reports showing the real key quality parameters in your camera. And in the end, I hope that you choose the best Scandinavian supplier, of course.